In section 5.2, we're going to consider something called random variables and explain the basics of a probability distribution. Let's start out with a definition. A random variable is a variable that has a single numerical value for each outcome of a procedure. A probability distribution describes the probability for each value of the random variable. It is usually graphed or put into a table. For example, suppose we roll a pair of dice and add them together. We'll let x be the random variable. Then x can take on any of the following values: 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. A discrete random variable has either a finite number of values or it's countable. Similar to our discussion about discrete data in previous sections. A continuous random variable has infinitely many values, and those can be associated with measurements on a continuous scale without gaps or interruptions. Is the following a discrete or continuous random variable? The number of people driving a car right now. Well, since we could actually count up the number of people driving a car right now, this would be a discrete random variable. The weight of gold stored at Fort Knox. Well, the weight could take on any value between two integers, so we'd consider this to be a continuous random variable. The height of an airplane. Since height can also take on any value in between two integers, we'd consider this a continuous random variable. How about the time it takes to fly from LA to Shanghai? Well, this could be, we'd have to be careful, because if we're talking about the number of minutes, we can count up each minute. However, if we're talking about the exact time it takes, time could take on any value between two integers, so in that case, I would consider this a continuous random variable. The amount of milk we get from a cow could also take on any value between two integers. So this again would be a continuous random variable. The number of whole gallons of milk from a cow. Now we're talking about whole gallons, so there would be 1 whole gallon, 2 whole gallons, 3 whole gallons. In other words, we can count them up, so I would call this a discrete random variable. Example, count the number of people who walk into a convenience store during an hour-long period. 1, 2, 3, 4, 5, 6, 7. This is discrete. Measure the amount of coffee you drink in ounces during a day. So of course, this could take on any value between two integers, so we consider this to be a continuous random variable. Here is one way to describe a probability distribution as a graph. Notice that the probability of 0 is represented by the height here. We might say the probability of 0 would be 0.11. Or another way to say it, more exact, is the probability that our random variable would take on the value 0 would be 0.11. The probability that our random variable would take on the value of 3 would be 0.2. So the probability that our random variable takes on any one of these values is determined by the height of the bar that is representing it. A couple requirements that must be met for something to be considered a probability distribution is that the sum of all the probabilities must be 1. Also, any individual probability for any value of our random variable x has to be between 0 and 1. So consider the following table, and does it represent a probability distribution? Well, at first glance, the left column seems to represent a random variable because our random variable can take on any single numerical value. And in the right, we have several what seem to be probabilities that are between 0 and 1. To have this table represent a probability distribution, however, it would have to add up, the probabilities would have to add up to 1. However, if you actually add these up, they only add up to 0.91, not 1. So this would not be a probability distribution. If we're given a probability distribution, we can find the mean, the standard deviation, and the variance of it. The mean is calculated by taking the random variable values and multiplying them by the probability that our random variable takes on that value. And then finally adding all those calculations. The standard deviation has, again, just like we saw before, two separate formulas that give us the same result. So one option is, under a square root sign, we could add up the difference between our random variable values and the mean that we calculated with our first formula, squared times the probability that x takes on each of those random variables, or each of those values. Alternatively, we could take, under the square root sign, add up the value of our random variable squared times the probability that our random variable takes on a value, add all those up, and then finally subtract off the squared value of our mean that we calculated with our mean formula. And similarly to before, when we talked about standard deviation and variance, the variance is the same calculation as the standard deviation, we just don't take the square root of it. So for example, if we had this probability distribution and we wanted to find the mean and standard deviation, let's first calculate the mean. To do that, I'm going to take 0 times 0.3 plus 1 times 0.5 plus 3 times 0.2. Adding up each of those terms gives me 1.1. Now, for the standard deviation, for this example, I'll use this formula. So what I'm adding up are my x squared columns, so the values of my random variable squared, and each time I square it, I multiply it times the probability that my random variable would take on this value. So that is 0 squared times 0.3, 1 squared times 0.5, plus 3 squared times 0.2. Then I subtract off the mean squared that I calculated earlier, 1.1 squared. So finally, I take the square root of 2.3 minus 1.21, which gives me 1.044. The rare event rule. Consider if we are told that a coin is fair, the probability of getting 937 heads out of 1,000 tosses is extremely small. If we actually got 937 heads out of 1,000 tosses, we could assume that the coin is not fair. X successes among n trials is considered unusually high if the probability of X or more successes has a 0.05 probability or less. So back to the example with the 937 heads, it's unusually high number of heads because the probability of getting 937 heads or more out of 1,000 tosses is less than 0.05. So consider this probability distribution. Is 1 an unusual value? Well, to answer this, we simply have to add up the probability of getting 1 or less. That is, the probability of getting 1 plus the probability of getting 0. 0.3 plus 0.1 is 0.4, but that's greater than 0.05. So getting a 1 would not be considered unusual. How about this probability distribution? Is an 8 unusual? Well, following the same idea, except now we want to know the probability of getting 8 or more. If the probability of getting 8 or more is less than 0.05, then this is unusual. So the probability of getting 8 or more is the probability of getting 8 plus the probability of getting 9, which only adds up to 0.01, less than 0.05. So we would say 8 is an unusually high value. The range rule of thumb says that the maximum usual value should be about the mean plus 2 times the standard deviation. And the minimum usual value should be the mean minus 2 times the standard deviation. So let's calculate the maximum usual value for the probability distribution we just saw. Well, a simple calculation based on our previous formula would give that the mean is 4.05. Similarly, we'd calculate the standard deviation to 1.89. So the maximum usual value would be 4.05 plus 2 times 1.89, and that equals 7.83. So when I asked a second ago if 8 was an unusual value, here we calculated that the maximum usual value would be 7.83. Anything greater than that is probably going to be unusual. Expected value. Expected value is the sum of the value of a random variable times the probability that the random variable takes on that value. The expected value is often used in calculating expected winnings from a lottery game. So consider this example. If there's a game that costs us $5 to play, and the probability of losing is 37 out of 38, and suppose we win $180 but it costs us $5 to play, then we're really only winning $175, and there's only a 1 out of 38 probability that we would win. So to calculate the expected winnings, I simply need to multiply the value of my random variable times the probability that the random variable takes on that value, and then add those up for winning and losing. So the negative $5 times 37 over 38 gives me negative 4.87. And for the winnings, I multiply 175 times 1 out of 38 gets me 4.61. So my expected winnings over time, if I played this over and over again, would be negative 26 cents. This means that if I played enough over time, and really it means if I played infinitely many times, then I could expect to lose 26 cents each time I played. Now, of course, sometimes I'd win and make $175, but more often than that, I would lose $5. So my expected winnings over time would be negative 26 cents each time I played. Again, let's try this one. Now this one is slightly different because we only win $5 if we win. But the probability of winning is so much higher than in the previous example. So think about what this means. This again costs me $5 to play. If I win, they give me $10, but since it cost me $5 to play, I really only win $5. So again, if we multiply the value of our random variable times the probability that our random variable takes on that value, and then add those up for the win and losing rows, in this game we could expect to lose 8 cents each time we played, assuming we played over and over and over again. In New Jersey's Pick 3 lottery, you pay 50 cents to select a sequence of 3 digits, such as 332, 121, 578, etc. If you select the same sequence of 3 digits that are drawn, you win and collect $400. The first question to ask is how many different selections are possible? Well, if we're only picking 3 digits and each of those digits have 10 possible digits to select from, 0 through 9, then we simply have to calculate 10 to the third, which gives us 1,000 different selections possible. What is the probability of winning? Well, if there are 1,000 possible combinations of 3 digits, and only one of them will win, the classical approach to probability gives us that the probability of winning is 1 over 1,000, or 1/1000th. If you win, what is your net profit? Well, of course, since we're collecting $400, but it cost us 50 cents to play, we have to subtract 50 cents from the $400 we won, so we're really winning $399.50. So the final thing we want to calculate is what is our expected winnings if we played this over and over and over and over again. So to do that, we want to calculate the cost of losing, or 50 cents, times the probability that we lost, and add that to the cost, or the amount we'd win, times the probability of winning. Plugging all this into our calculator gives us that we would win negative 10 cents, or in general, over time, we could expect to lose 10 cents each time we played.